Hi, ladies and gentlemen. Thank you for being here today. I wish I could be there with you, but we're all virtual, and I am virtually virtual as this is pre-recorded. But my name is Emily Cole, and I am the Climate and Agriculture Program Manager for American Farmland Trust here in New England. I work out of their Northampton office, or our Northampton, Massachusetts office, but I'm actually a Connecticut resident. I live up here in Simsbury, so wish I could be there for you, but I am going to take you down a little bit of the science background as to why no-till is great and what it can do for soil health and soil resiliency. So I am going to share my video. So in today's day and age, we're seeing a lot of disturbance in our normal growing patterns, in our normal seasonal warm-ups and cool downs, in precipitation, and also in disease and pest issues. Unfortunately, that is due to the inability all around to adapt to climate change in a rapid manner. It is not how plants work. It's not how people work. And so what we can do instead of trying to adapt on a timescale that's infeasible is we can think about what processes and what types of practices can we put into place now to actually better prepare us to be more resilient, and then eventually start to be able to actually mitigate the impacts of climate change. So to get started, I'd like to define resiliency because it is somewhat sort of organizational, sometimes it's even personal. And so I'd like to define it as the ability to maximize and continue use of the ecosystem services on the land. And ecosystem services, for anyone that's unfamiliar with that term, it's all of the things that humans depend on that we get from the land. So it's food and fiber, number one for sure, and fuel, but it's also temperature regulation. It cools the air. There's gas regulation, right? We know that we have plants that will give us the oxygen, and they're taking in the CO2, so there's that gas regulation. But it also filters and cleans water. It stores water. It's a habitat for biodiversity and for animals that are essential to humans. And so if we are trying to maximize and continue the use of those ecosystem services, we have to be resilient. And so I'm going to use resiliency in the form of being able to reduce vulnerability to some of these risks, but also to increase our capacity to adapt down the road to these risks that are becoming more and more common. And what are these risks? So I alluded to a couple of them before, but drastic temperature changes. When it's 75 during the day, and then you have to go cover your tomatoes like I did the other night because we're going to have a frost. A couple weeks early than is normally expected for where I am. Also, we had some really drastic areas lacking water, so we're seeing drought issues. On the other hand, sometimes we have a very wet spring, and so we have significant flooding. And it's not only just that we have periods of dry and periods of wet, but the actual precipitation events that we are seeing are more severe as well. And so we're seeing more damage just due to things like hail or inopportune timed freezes, like we saw with apples just a couple of years ago. Other risks that we see that we're trying to reduce vulnerability to include erosion, disease pressure. I mean, that could be fungal, it could be quite a few different things. Pest pressure, seeing invasive insects come in and do quite a lot of damage to crops, weed pressure, and all of these together can lead to soil degradation, which ultimately leads to crop loss, whether you're a diversified vegetable operation, or if you're trying to grow large row crops and field crops to either feed your animals, your livestock, or for production itself. And so when we're thinking about this degradation that can occur because of really a lot of different factors, I like to bring up this image, and it's a couple of years old. It's like 25 years old, but I think it illustrates this just perfectly. When we have more traditional types of agricultural practices that usually include intensive till, oftentimes will also include significant inputs into the soil. And, oftentimes those soils are left bare for a good portion of the year. Those practices together do a number on the soil health almost immediately. As soon as you begin tilling soil, it begins just pouring carbon dioxide into the atmosphere. When that's happening, that carbon dioxide is coming from the organic matter that was in the soil. And organic matter is a lot of things. It's partially decomposed roots and leaves. It's the living bacteria and fungi. And then it is a whole mess of these chemical compounds that are varied. We don't even have a specific formula for them. It's just that there's sort of this range of really well decomposed organic matter that we call humus, fulvic acids, and humic acids that are really the stable part of the carbon in the soil that is so essential for having soil that can be resilient to climate change. So when we continue to practice intensive till on soil, what we see is the loss of organic matter, which causes the loss of really soil structure and the breakdown of aggregates in the soil. Then we get crusting, we can get compaction, and when we have crusting and compaction, it's difficult to farm, it's difficult to have water infiltrate, and what that means is greater risk to water erosion. And with every drop that's moving soil along with it, that's more loss of organic matter, it's more loss of your topsoil where your nutrients and your biology is. And the more that happens, the greater likelihood you are to have poor structure and greater loss due to erosion. And then you start seeing crop yields reduce. And then you see crop yields or crop quality reduce and suffer because of this. The downward spiral here is almost immediate when you begin really opening up and churning the soil and exposing all of that organic matter and all of that bacteria to oxygen. Because as soon as they get oxygen, it is like a kid in a candy store and they will eat everything in sight. They'll get all of that extra energy and they will decompose all of that organic matter and you'll lose your structure. And it's really an immediate consequence that you see happening. So in all of that unfortunate downward spiral, organic matter is really one of the key factors that we're trying to protect in better management practices on soil. And increasing organic matter, or even just trying to maintain, number one, the organic matter you have, and then learn how to try to actually increase the amount of organic matter you have, means you will have enhanced drought, flood, and heat resilience. You'll have better water infiltration and retention due to better structure and better aggregation. That means reduced soil erosion. That means better water quality in your area. That means reduced nutrient pollution. And then what we also see is increased biodiversity, increased biological activity. We see really better use efficiency of the nutrients that are in place, which will reduce your need for any external inputs. And all of this together, the more you can protect and then improve these is just the more you're going to be able to increase productivity and increase resiliency. In the manner of protecting and increasing resiliency of your soil, this image comes from the NRCS, and what you see here is really there are four, well, it's really five, I'll get to five in a second, but there are four pathways to really improving soil health. Two of them are really about feeding, and two of them are about protecting. And so I'll talk about feeding first, and then we'll talk about protecting, which is really what no-till is. It's protecting the soil. Feeding the soil is not about inputs. It's about plant matter. And so having constant plant matter that can grow and bits of it can decompose. It can prime the soil biology and the soil microbiology to improve their ecological dynamics and improve their food web. And it's about giving the organisms in the soil the nutrients they need, the sugars and the carbohydrates that they need to then organically provide the nitrogen and the phosphorus and the other nutrients that the plants need back. When you have a really well diversified soil ecosystem, you have a really well tuned relationship between your bacteria, your fungi, and your plants. Another way to feed would be, crop rotation, where you're diversifying the plants that are actually in it. Perennial vegetation, where you're constantly keeping something in there. That is just amazing. If anyone's ever seen images of the grassland soils with perennial grasses that have 2-meter long root systems, pretty amazing to see. And that's the potential you get with perennial vegetation. Pollinator planting is another way to feed and really diversify what you have in your soil. And then rotational grazing is another way to really feed your soil with the introduction of livestock, whether it's large or small animals. You're going to introduce manure, which primes different sets of bacteria and fungi and brings their own sets of microorganisms to the soil, and it really just enhances the biodiversity that's available there. It's also a really good way to put carbon back in without having to really try to think about remaining residue on there. If you need to feed your organisms and they're feeding on the forage that's there and they're leaving manure, that's a great way to get that carbon back in there. The other side of this image is the protection of soil side, and that's minimizing the disturbance and that's maximizing the cover. And no-till is an opportunity to do both of those. You are keeping the soil intact. You're not slicing it open and churning it over and exposing all of that bacteria to the added oxygen source, where they're going to really just eat up all of the soil carbon that they can find. You're keeping it covered. You're keeping that environment underground with limited oxygen, which keeps that bacteria and fungi in check. The other thing you're doing with no-till is you are maximizing the cover. If you're not tilling, then there are still going to be some sort of stubble on the surface of your soil, and that's great. Living plant material is by far the best, but even dead and decaying material that is, think about like corn stover stubble on a field, even that is a benefit to your soil when you're not actually growing your cash crop. A couple of other ways that you can protect: controlling traffic, making sure that when you have a really wet, mushy spring, that you are being very careful and planned about when you access the field, especially if you have large equipment. Other ways to maximize soil cover, I'm sure today's no-till, but also cover crops are just an amazing asset to the soil. Not only do they protect it, but they can actually return and improve the soil health while you're not growing your cash crop. It's pretty amazing. Okay, what we're going to have here on this next slide is what's called a rainfall simulator, or rainfall simulation, and you're actually going to be able to see the impacts that water can have on 4 different soil types that have been very recently tilled, sort of mid-range tilled, and all the way to something that has never been tilled. And you'll get to see a real clear picture visually of what happens here with water in these 4 different situations. And so what you can see right here is a setup where there were 4 bins, and the first bin had this sample of soil from a field that was tilled 2 weeks ago. The next bin had something that had soil that was tilled 10 months ago, and it did have some cover crops on it. Then the third one is tilled 22 months ago, so almost a full two years, but then also with residue and cover crop. And then lastly, we have the never tilled hedgerow at the edge of the field, which has been in perennial vegetation for the whole time. And so these samples of these 4 different fields have been basically sliced out with some shovels and put into these pans. And what you can see here is that they are pouring water slowly in the top clear container, and that container has a bunch of small holes drilled into it to then simulate the drip of rainwater onto the surface of these 4 demonstration soils. And what we're looking for is to see what's the difference in the water that actually is going through the soil down what would typically be groundwater, what is running over the surface of the soil, which will come out into those 4 front clear containers that you can see, and what is staying held within the soil. And we'll actually be able to see the difference of this pretty clearly in just a minute. And so as they get towards the end of their cups of water, you're going to begin to see the runoff of the 4 soils into these front pans. And so the first and the second certainly have a much steadier stream of water coming off of those. And just as a reminder, that's the one that was tilled very recently with nothing on it. And then the one that was tilled 10 months ago is the second one. And you can see right away the difference in the quality of the water coming off the surface as compared to the last two. And the last two, it's the third one is the 22-month ago tillage, and then the last one with that green lush plant matter is the hedgerow. And so what you can see here, in terms of the numbers, it's pretty clear that the sample that was very recently tilled had 240 milliliters of water run off the surface, and it was very brown in terms of the color. Then the 10-month ago had about 2/3 of that amount of water run off. The sample that was tilled almost 2 years ago had very little, 1/10 of the amount of water run off the surface, and then the one that was never tilled had almost nothing. And so looking at surface water, what we see here is protection from surface water erosion in the two samples that had not been tilled and the one that had been tilled almost 2 years ago. Not only is that water going somewhere else, but that is soil that is staying put, that you're not losing. The water that infiltrated, so that's the water that actually goes down through those soils and would actually collect in a bottom pan. So that would be like the groundwater recharge. You could see that there are some differences, not as significant as the other. And the one that was tilled 10 months ago actually had a little more actually move through it. When we look at the tilled 2 years ago and the never tilled for that, we see almost 3 times as much move into those. So whether you're tilled 2 weeks ago or 10 months ago, you're still seeing a sort of similar impacts on the water infiltration. But when it's been 2 years or never, you see significant improvement in how much water can move through. And then in the bottom, that water absorbed, that's how much actually stayed within the soil. And so a little bit of difference between the 2 weeks and the 10 months ago, for sure. And then we see not a whole lot of difference across those. And so what we see here in this visualization of that is a no-till environment that allows water to move downward through a lot of different processes. One, there's a lot of air and space around the aggregation. You've got really good structure. But then two, when you have a really healthy, diversified ecosystem, you've got lots of good things like worms that dig, burrows, and that actually is a great way for water to move into the soil. On top of that, when you have vegetation or stubble, it slows that water down, providing a greater opportunity for it actually to enter. On the other hand, we see this tilled ecosystem where you have very poor structure. It's pretty uniform in color. You could pick it up and it would sort of crumble. You don't see a lot of fine roots holding pieces together. You have a nice crust on top, especially when it's been dry. I'm sure a lot of you have probably seen that in your fields. That's what really doesn't allow water to get into the soil, and instead we see it running across the surface, pulling that topsoil away with it. And then what you see here is visualization of this no-till versus conventional till. The bottom, you can see the no-till with all the stubble and the cash crop planted within the stubble with very little water standing on it. But at the conventional till, you see a really soggy surface where that water cannot infiltrate. Above it, you see this really lush green. Well, that farm uses cover crops and no-till. If you look on the other side where you have the chisel disc use, not only is it less green, I'd like you to see the difference in the width of the stream that runs from the lush green field into the chisel disc field. What you have there is stream bank erosion because that soil is not being as protected as well as the other side with the cover crops. And so you're losing soil. That stream is carving out more space from your field, and you are really just watching your profits and your plant health and your soil health drift downstream. This is another USDA resource. This is a slake test, and this is just a good visualization of what structure can do with water when it's really nice structure with lots of organic matter, or when it is real poor structure, things that have been tilled a lot without a lot of biological health. And what you see this conservation planner do is she's going to take these 2 clods of soil. That one that she just held out has a lot more organic matter. It's been under no-till, even though it's been continuously cropped. The other one is been traditionally tilled, and when it's not cropped, it's fallow. So we're leaving it open and exposed. Visually, you can just see the difference already. One looks like a solid mass, and one looks like it has some space in it. And now what you can see, and I'll pause it for a moment, is the difference of the two when they're in water. The tilled crop fallow immediately begins losing particles, really just to gravity and water being able to get in there and separate pieces from each other. And the no-till continuous crop is really staying very much intact. Those are the fine roots. Those are all the various compounds that soil roots exude. That's, you know, the fibers of, or the filament of fungi holding this all together. That is good structure. And that is what allows water to move through it, not destroy it. And unfortunately, when you have poor structure, water can do a lot of damage. So what we see here is that no-till itself has a great impact, but ultimately it's about being able to maintain soil organic matter, which leads to better structure, leads to better biodiversity, leads to greater nutrient efficiency, and really leads to greater benefits overall, because ultimately we're leaving that carbon in the soil where we want it. And the more organic matter we build, the more carbon we're pulling from the atmosphere and down into that soil. We're becoming more resilient, our soils are becoming more resilient, and at the same time, it's an opportunity to draw down that carbon and do every small part that we can to mitigate the greenhouse gases and to mitigate climate change impacts. Thank you all. I hope you all enjoy your virtual field day, and I wish I could be there virtually with you all. I appreciate your time. I, again, am Emily Cole. I am from American Farmland Trust. I'm the Climate and Agriculture Program Manager. And if you have any questions, please don't hesitate to reach out. My email is ecole@farmland.org. Thank you.